Hi, my name is Mohammadreza Zarindast, and today I'm going to talk about algorithms that has been used in structural analysis, which is a semester project of parallel processing course, which is lectured by Professor Savadi, and I hope you enjoy it. Okay, first we're going to break the structural analysis into key steps, and after that I'm going to show you the pseudocode that run the algorithm in series. Okay, the method that I've been used in this project is finite element method, which is involves in several algorithms and each serving a specific purpose depending on the nature of problem and the domain of our applications. And there is a review of the steps, the key steps that we're going to cover in this presentation. The first is mesh generation. It's not exaggeration if we say the mesh generation method is the most important step in finite element method because if you have an accurate, very distributed mesh, you can expect better results. After we generated the mesh, we can go to the next step, which is a stiffness matrix. And now we have elements, we have many elements. We're going to put them in a matrix and multiply them other constants to build our stiffness matrix. And when we have our stiffness matrix, we can apply our boundary conditions. uh, some of the rows or columns of our matrix going to be changed. We have many boundary conditions. It can be load, it can be pressure, it can be other constraints. Next, we're going to solve the equation. We have a matrix that we're going to solve it and measure the U. After we solve the equation with a specific solver, we're going to use the results to measure some other constants or some other variable or other quantities like stress. In short, mesh generation means discretization of shapes into elements. Okay, one method is to use Delaunay Triangulation, which used to set up points, subdivide their convex hull into triangles in a way that circumcircles do not contain any of the points. Point of this approach is to maximize the size of the smallest angle in each triangle and tends to avoid sliver triangles, which help us to have a distributed triangle. But it's a tough decision to detect when a point is within a triangle circumcircle or not. There are many ways to apply Delaunay triangulation, and we have to consider two things. The first is we have to assume the time complexity of that operation that should be low, and also the data structure that we're using for that is should be efficient and use less memory. One way that I'm going to use in this project is evaluate the determinant of matrix. If it's if it's greater than 0, then the point D is not in the circle of triangle ABC. And if it's lower than 0, then we can assume that the point D is in the circumcircle of triangle ABC. So we have to change the points to change the triangle edges to find the triangle that satisfies the Delaunay triangulation. Okay, now we know the algorithms of the Delaunay triangulation, but we have to consider how we insert the points into our geometry. For example, the first one is edge flip. You insert all points at the same time at the first of processing, and then calculate the Delaunay triangulation one by one. And the other approach is to use Boyer-Watson, which is faster than edge flip. It's use incremental method and insert point at a time, repeatedly insert point at a time, and uh, re, mm, and the total time complexity of this approach is O n log n. Another approach is advancing front method, which is also an incremental method, but the difference is we add the new triangles start from boundaries instead of selecting them randomly. And prioritize boundaries, conformity, and local operation. And it's also efficient in local operation and reduce the memory usage. One thing we can do is to use divide and conquer, which helps us to run the process in parallel, and also it's more efficient and faster than other methods which can combine with them also, and it's decompose the domain into some smaller elements and solve the equation for each of them, and finally mix them. Here you can see a comparison between Boyer-Watson method and the advancing front method. And at first you can see point placement strategy, which is sequential in Boyer-Watson and depends on boundary in advancing front method. Data structure that is used is list in Boyer-Watson and a stack in advancing front method. The time complexity is the same. Worst case is O and 2 and optimized time complexity is O n log n. And performance is compared. uh, Boyer-Watson method is more robust but expensive. It uses more memory. And advancing front method is reduced memory requirement, but sometimes it may be not be robust. Here we can see the pseudocode of Boyer-Watson approach. At first, we analyze an empty triangulation matrix, and for each point that we add to the mesh, we locate the triangles whose circumcircle contains the new points and delete those triangles. And from the new triangles connecting the point to the boundary of deleted triangles, form it and check if it's Delaunay or not. And you can see the advancing front method pseudocode, uh, which is have a initialization at the first step, and it's use a stack to store the points, and when the stack is empty, the process is done. And it's as you can see, it's more efficient than Boyer-Watson approach. Now we are going to talk about the stiffness matrix assembly, which is computing the global stiffness matrix for the structural analysis. As you can see in the pseudocode, we have a K global, which is a matrix the size of our nodes, and we have a for loop on our elements that we discovered in the previous step, and we calculate the stiffness for each of these elements, finally assemble them into the K global and return the K global matrix. The next step is to apply boundary condition and enforcing boundary condition on the geometry. And in the pseudocode, you can see some changes that apply to stiffness matrix, and some values are changed. For example, fixed nodes are added to our stiffness matrix, and also some conditional loads is added. Finally, we're going to solving our operations or solving our equation, and the formula you can see there is K multiplied by U is equal to F, and we're going to solve this matrix equation. And also, optionally, we can compute derived quantities like stress or other quantities after the processing. And as you can see, this step is very look like the calculating stiff matrix. And for each element, we're going to compute stress based on the U that we have discovered in the previous slide, and we return the stress fields. And you can see the references that I use in this presentation, and I hope you enjoy, and thank you so much for watching.